Hello and welcome to another episode of Between Two Nerds, where once again we have invited a small human being to sit between us and have a little chat about science. And in this episode, our human being is...
Elyes, and I'm 10 years old, nearly 11.
We had that discussion. We think he's 24th of his way to being an 11-year-old. Congratulations.
Yay! And you know the nerds, I am Mo.
And I am Eugene.
Thank you for that.
Thank you. Did I get a little, little jazz hands? Yeah. I like a little jazz hands.
Okay, so fire away, Elyes. You've come prepared.
Oh yeah, I'm slightly intimidated for this one because Elyes has brought 3 pages of notes.
Actually, I think I brought...
2 double-sided. Sorry.
4 pages and 1/2 of a page.
I'm more intimidated by what's in your head, to be honest, but let's see where it goes.
Alright, so first question.
What makes black holes so heavy? I get that it accumulates matter and, well, makes it incredibly dense, but what makes them so heavy?
Correct. Next question.
I think we should first start with what is a black hole? Yeah?
So if we talk about black holes, well, there are loads and loads of black holes. And black holes is a really interesting one from a science perspective because
It's a mystery.
Well, it's a mystery, but it's an unraveling mystery. So if you take the last sort of 2-3 decades, thanks to a lot of the cool stuff that we've been able to build and make and stick in space, our understanding of black holes and frankly our awareness of black holes has increased massively over the last couple of decades and will continue to do so. But what is a black hole? A black hole is a super heavy object. Very, very dense object. Huge amount of mass. And
with lots and lots of gravity.
Loads and loads of gravity. So there is a black hole in the center of our galaxy.
Supermassive one.
Yeah.
Supermassive, but there are way, way bigger ones out there. There is a big black hole in the center of our galaxy. And the same way that the sun has a gravitational pull.
It's in the center of the solar system.
Absolutely, and the sun kind of holds our solar system together. The black hole at the center of our galaxy kind of does a very similar job, and that's the reason that our entire galaxy kind of rotates and orbits this black hole in the center. If we think about gravity and what makes a black hole so different to, say, the sun or a planet. So what gives something its gravitational force, do you know?
The how tightly the atoms are packed together.
And how many. Yeah. So that it's density and its mass. So if you take planet Earth, it's a huge object. It has enormous mass. Huh?
But it's not very dense at all compared to a black hole or the sun.
Yeah. Relatively speaking.
But compared to you... very heavy. Right?
A great way to visualize this. So, if we had a big trampoline in front of us, and so don't think of it as the universe, think of it as literally a trampoline, one of those small ones that you exercise on, or a big one, whatever like trampoline you like. Now, if I got an apple, which has mass and is kind of planet-shaped, and I dropped it into the middle of that trampoline, what is going to happen to that
tiny indentation.
Absolutely. So you're going to see a little curvature of that trampoline.
The trampoline is
centering
space-time?
Where that... Absolutely. Yeah. So yes, imagine...
So it bends space and time?
Yeah, correct. So Einstein called this... Okay, so here, the trampoline fabric in our example, they call this the fabric of space-time. So he took space, the thing that we move in, and time, put them together in something called continuum. And so there's 4 dimensions now, 3 of space, 1 of time, and this is the fabric of our reality, of our universe, right? And it stretches.
So it stretches, so we've got the apple. Now let's take the apple away and replace it with...
A bowling ball.
A bowling ball. A bowling ball that we've squished down. So let's say, an elephant. Let's take an elephant, squish that elephant in something that fits on the trampoline in a sort of spherical way, drop that in the trampoline. What is going to happen to that trampoline this time?
The trampoline will either fall to the ground and...
For this one, we're going to have to imagine there is a hole in the ground so the trampoline can stretch as far as it needs to stretch.
It will sink extremely far before
way
finally
So it
ripping.
curves even more, right?
And what
Before
happens, so if you're another object, so if you're a planet, or if I'm going to use the fruit, if you've got the apple there, and I'm a grape travelling across that trampoline, that little curvature that centres itself around the apple, that's going to pull me in. So I'm going to get attracted to that apple depending on how fast I'm going. So with the apple, where we don't have a huge amount of bend, a huge amount of curvature, that grape has a reasonably good chance, if its speed is high enough, of rolling. It may move slightly the way it rolls and rolling off and coming off that trampoline. Now, if we take our elephant, we've got much more curvature.
Then
Something
everything
coming
on the
past is
trampoline
far more likely
fall
to
on
get
the elephant.
stuck, trapped in that curvature and spin down or fall down and join our squished elephant. Now, if we take a black hole, we take that same thing, you've got the same trampoline. Now let's imagine we've taken the entire planet Earth and squished it down to something about the size of my head. So that's going to be quite hard to lift. But let's imagine we can lift it. And we put that in the middle of the trampoline. So can you imagine now what's happening to that trampoline?
Well, it would probably get bent, but in a very, very thin way.
Yeah, we'd get it a very thin way. And right down at the bottom of that curvature, if we take the way that we're visualizing that trampoline, the sides of that curve are going to be pretty vertical. Now, anything that finds its way there isn't going to be able to get out. It is trapped. And that's kind of a black hole has that amount of mass that it affects and impacts the curvature of the trampoline, which, as you rightly said, is the curvature of space-time, to the extent that its trap is huge. So if anything gets too close to the way that's curving, there will come a point which we call the event horizon. And we call it the event horizon specifically for light. So light, that travels pretty quick. So the quicker you're going, the less likely you are to fall in. Now, nothing travels faster than light. But this has stretched and bent, curved space-time to such an extent, it's got so much mass, that light travelling across that trampoline, that gets to the point where even the speed that light's going, it cannot escape. It's now falling. So that point where light cannot escape the curvature of space-time, we call that the event horizon. And inside that, once you're inside the event horizon, frankly, we know pretty much nothing. And there's a very easy reason that we know nothing. Because
nobody's been inside and nobody's come out. And
even if you send someone in there, they're never coming out. And even if you sent a probe that could tolerate that gravitational crush, which is very unlikely, but even if it could tolerate that crush, how is that probe ever going to get a signal out of the black hole? Because nothing, including light, is capable of escaping. Yeah. So that's a black hole in a miniature nutshell.
Yeah, so honestly, we didn't even know that these existed. They were first theorized, I think, by about 100 years ago by William Herschel. We called them dark stars. He thought that they might exist. And it's only in the last 50, 60 years that we've really found more. We didn't even know if they would, even if they did exist. Now, how do you see a black hole? Why is it called a black hole?
Because you can't see it, because light can't.
So I can see you now because light is hitting your face there, bouncing off and coming into my eyes. Now if light hits this black hole, it's not getting back out. So that's why we call it black. Okay, so you can't see it.
Will you just see right through it?
Well, they have actually tried to do... so you do see something, though. Now, this is Stephen Hawking. You've heard of Stephen Hawking,
yes,
right?
I've read his book.
Yeah. With a brief history of time?
What was it called? The
Brief Answers to the Big
Questions. Great.
Yeah, so there's this thing called Hawking radiation. So even though a black hole doesn't give off light, there are particles that come into existence, in and out of existence, inside and around this black hole. So it does radiate off these particles. We call this Hawking radiation. So there is something that you do see around the black hole. It is, but even when you do see it, so it's like a ring of radiation around it. But when you actually were to look at a black hole, so they've taken a picture just this year, took a picture of it. And what you're seeing is actually, so imagine that's your black hole. Now, it actually just doesn't look like a little disk. It's like a sphere, right? And there's this ring around it, like the ring of Saturn, let's say, but of radiation. But at the same time, you're actually seeing the front of the ring facing towards you, and you see the back of the ring at the same time.
How is that possible? Black holes are transparent?
No, because the light escaping from that radiation... Okay, so remember, space is warped here. So the light traveling actually bends. It's called gravitational lensing. This actually happens... like around the sun or a star, something with lots of gravity, that light coming from something behind that star can actually bend around the star and still get to you. Okay, so imagine you're a star and there's something behind you there, right? Light coming off of it, if you have enough gravity, can actually bend around you and still get to me. And because this has so much gravity that you're seeing the back and the front of it at the same time.
Which makes no sense because the light should have been sucked in.
Yeah, but then that light hadn't fallen into the event horizon.
Yet.
Yeah, but it's outside the event horizon, so it's fine. It's going to get past. It will just get bent as it goes around.
The fact that we can see that light, tells us that it did not cross the event horizon. Otherwise, it would just be the blackness.
Inside that, you're not seeing anything at all.
Now, Elyes, so if we imagine back to Herschel's trying to figure all this out, and he's come up with his theory that these black holes exist, has he just made that up, do you think? Or does he have a reason?
He has a reason, because... Oh, no, that was the dark matter explanation.
Well, actually, it's very similar to the dark matter explanation.
Because something must have been holding the other things together, the stars together, the planets together.
So we had an understanding, and we had a growing understanding of why stuff in space and stuff anywhere, but if you take space, why the solar system behaves the way it does, what impact gravity has. And what we were starting to observe was the sort of response to black holes, a bit like you've just mentioned dark matter. So dark matter we know nothing about, but scientists theorize that it must exist because we see its impact, we see its effect on everything else. So something is making stuff. So with dark matter, something is making things expand away from everything else. With black holes, something, as you rightly just said, is kind of holding all this stuff together. And the way that the stars are moving within our galaxy must mean that there is something causing that. And that is where he started theorizing, and then we started kind of hunting to prove that these black holes exist.
Yeah.
Which is cool.
Which is very cool. Yeah, so that's how they discovered the one in... So we haven't actually seen the black hole in the center of our galaxy. Was it called Cygnus? Sagittarius.
It's one of those moments where whatever you say, I'm going to nod.
So the black hole, supermassive black hole in the center of our Milky Way galaxy. We can't actually see it. We don't see any Hawking radiation because it's just not close enough, I guess. But what we're seeing is that stars around or close to it are behaving in a way that suggests there's an incredible amount of gravity in the center there. So we're seeing the effects, and that's how we know that it's there. And judging by how they're moving, we can also know how much gravity is there. And because we know how much gravity is there, then we know how heavy that black hole is, how massive it is. That's a super massive one. And the idea is, what do you think would happen if you were... Let's imagine we're floating around in space, and we're right next to this cool big black hole, right? And I give you a little push.
I'm getting in.
Right? Yeah. Who's first, right? Let's see who's going to jump in.
It's fine once you're in.
Yeah. All right, so I give you a little push. What do you think might happen?
Spaghettified.
Spaghettified. So you've heard of spaghettification, right? So what's happening here now, because this bending of space-time is so steep, right? So let's say we fell in feet first, okay? Now there's an incredibly large, the difference between the amount of gravity at my feet and at my head is huge. Right now, it's also different because my feet are closer to the Earth than my head is. But the difference is so small, it makes absolutely no effect on us, right? But in a black hole, right, once you're inside that event horizon, even as you're falling in to the event horizon, there's so much gravity now that your feet would start to get stretched out, right? They're falling in faster than your head is, so you'd be spaghettified, is the scientific term that you know, right? And you'd be stretched into this infinite long human spaghetti, okay?
Sounds great.
And then, as you're falling in,
Doesn't sound
remember that that radiation around the black hole? Do you remember the Hawking radiation? So basically, a black hole you can think of is like you're falling into like this wall of fire. So once you're falling in, right, you're gonna get hit by all of this radiation and not be very alive, I'm guessing.
To be honest, there's very little fun to be had.
Yeah.
Black hole.
And then another part of this is so if I gave you a little push and watching you fall, actually though, when I'm looking at you, right, falling in, at some point it would look like you're just frozen there at the event horizon, not moving.
Forever.
Forever.
Because you're going because time starts to slow down. And the time slows down so much that one instant stretches on for infinity. So it's just like you're frozen in time there. And even for you there, it would just, that one instant would be frozen. That would be all of eternity.
It's a total rubbish.
Yeah.
Let's
So
not go.
who's jumping in first? You?
I did notice that in every example you gave, you'd given Elyes a little push.
Yeah.
I'd push him first.
But and then it would be cool. I mean, if we could just send something in there and get some way of sending that information back out, it would be just incredible. Because now
it's really dark in here, and I'm a bit squashed.
Because all of our theories of physics, science, break down at that instant. So there's no way for even for us to predict what would happen. Like, no one's been near a black hole, but we're already making all these predictions of what would happen as we fell in, right? But then at some point, once you pass that event horizon, all of our science just breaks. I mean, it just doesn't work at that level because now you're in this tiny, tiny region of space with this incredible amount of gravity. And there are two theories, right, that govern these two domains. So you've got Einstein's general relativity for the gravity part, and you've got quantum mechanics for the tiny, tiny, tiny space that you're in right now. And those two don't really work well with each other. Or they give us answers when we try to put them together. They give us answers that just don't make sense. So that's one of the biggest things that areas of study that scientists are trying to work on right now, trying to put these two laws, these two theories together and get them to work.
Or it should be. Should be one of the
yeah. So it's called this.
Not one of the
quantum gravity is what it's called. So that's where that's a very important part of our area of study for scientists at the moment.
Anything we don't understand, is a cool thing to study. Are you going to be a scientist?
Probably.
Yeah, good.
You've got the look. You've already got the look. I think that's half the battle. I never had the right look for science.
Why not?
Just worked on it. I haven't got the hair. All good scientists have got hair. Fact. Scientific fact. Name a famous...
you know what? I can't
yeah, exactly.
actually.
I can't. I can think of some famous swimmers.
Kip Thorne, who won the Nobel Prize for... I think he doesn't have hair. Sorry, Kip Thorne, if you do have hair.
Oh, congratulations, Kip Thorne, if you don't. Did you enjoy that, Elyes?
Yes, very much.
Good.
Right. So are you going to jump into that black hole the minute you get a chance?
No.
Are you going to push Mo?
Who's going to answer all your questions?
Maybe.
I'll wing it.
All right. Well, it was great having you on, Elyes. Great questions.
Thank you.
We will definitely have you back on.
Absolutely.
To answer the other...
I think through your... however many pages of notes it was, we've probably got through 2 of the sentences.
Yeah, we may have done 5% of those questions. And those weren't all the questions he had to begin with.
No.
Well, that was awesome, mate. Thank you.
Well done. Give yourself a little round of applause.
Yay! And should we wave bye? Bye, guys. Thanks
Thank
for
you.
listening and
Bye.
watching. Bye. Bye.
Right,
Love
another
you.
Big clap. Big clap. Bigger.
It's good.